This is Crawl 128, a very simple first-person dungeon crawler game for the C128's VDC chip. It doesn't look especially impressive. The interesting part happens under the hood. Because not only are games for the C128 in general rare, games made for the VDC chip are even rarer. I will talk a little bit about the game itself, and then I will give you some insights into all that unused potential of the VDC chip that could have been a serious gaming rival for the IBM XT. Welcome to the 8-bit theory. The spark that was to become Crawl 128 was ignited at the Dungeon Crawler Game Jam 2025, which happened in April of that year. A significant part of the game would require a first-person view, moving in squares only, and some combat mechanics. In addition to that, you had to pick one out of 3 themes, four actually: genre fusion, heist, sinking ship, or treasure hunting. Plus, you had to incorporate one or more chicken. And while I failed on multiple levels, like not finishing in time or incorporating that chicken, the result is still worth talking about, especially because of the C128. So, I was looking for inspiration. What could be done in the limited time frame of a game jam? I found a YouTube video about every 80s and 90s grid-based dungeon crawler. With a playtime of 2 hours and 54 minutes, I was pretty sure that I would find some inspiration. I was ready for a long evening. But there, after just 1 minute, 3D Munch was shown, a genre mix of Pac-Man and a dungeon crawler made for the Auric, another 6502 based computer. That was my inspiration for Crawl 128. The game is different to 3D Munch though, because I didn't even play it a lot, to be honest. Still, the goal is to collect all gems. The top line shows how many of these are still left, and there's also a ghost in the maze that wants to kill you. You can decide to evade the ghost or to fight it. If you kill it, the victory is only temporary. It will respawn and continue to chase you. That in itself is pretty simple, but it can be fun, especially when you try to collect all the gems with only a minimal number of steps. Each action takes 1 step, and that includes fighting the ghost. And while the ghost takes an action for every action you take, there is still ways to escape him. You're in for a challenge? Let me know in the comments what your lowest number of steps is. Now, let me tell you the nitty-gritty details of how the game was built, especially when looking at the VDC chip. Crawl 128 was basically written in Commodore Basic 7, but as everyone knows, there is no support for the VDC chip's bitmap mode in Basic 7. That's why I also used the VDC Basic extension. I'll explain the commands I'm using here, of course, but for a comprehensive explanation of its features, please feel free to check my previous videos. Also, the basic program is compiled by using the Blitz 128 compiler. That speeds up basic execution about 5 to 6 times over the original execution speed of a C128. And because we are not using the VIC-2 here, we are not limited to 1 MHz, and the program can run at a full 2 MHz. Here again, there's a dedicated video about the Blitz Basic compiler. Please feel free to check that out for more details. By the way, everything I will be talking about here requires 64 kilobytes of video RAM. If you ask me, shipping the 128 with only 16 kilobytes of VRAM is one major reason for the chip being hardly supported. Every C128 model can be upgraded to 64 kilobytes, by the way. Okay, this is the game's screen. The VDC chip doesn't have predefined resolutions as you know them from PCs. Pretty much every single aspect of the screen setup is directly controlled through the registers. But let's look at this screen and let me explain things as we go. The biggest part of the screen has a resolution of 160 horizontal pixels. Vertically we have 100 pixels, and below that it seems there is a higher resolution area that's about 20 pixels high and 640 pixels wide. Actually, the screen resolution is really 640 by 240 pixels, but we are using the upper region of the screen by means of a special video RAM setup that allows us to treat a 4x2 pixel block like one big pixel. That's explained in all these previous videos I mentioned. Each of these chunky pixels can have every color out of the 16 color palette. I call this chunky EGA, inspired by the term chunky VGA that made graphics on DOS PCs fast enough for games like Doom. The small text area below is using screen RAM and attribute RAM in the regular way, so we can work with 640 by 20 pixels here. Speaking of text, that's probably not very exciting to see here, right? But it is, because the VDC's bitmap mode does not provide text capabilities, so we really need to draw the letters as if they were regular bitmaps. The font I am using is taken from opengameart.org and you will find the link in the description. Every letter is 6 by 8 pixels. Looking at our chunky screen resolution, this means 3 bytes wide and 8 bytes high. I converted it by using ProMotion-ng and saved it as a regular bitmap file. That bitmap file is then converted to a character set file that's ready for VDC Basic's bitmap print command. I wrote that converter in Commodore Basic because that language has been stable for the past 40 years, so I don't risk running into broken builds or so, and it's part of the fun for me. On the left hand side you see the character set as it was defined in the bitmap. On the right hand side you see how the pixels are arranged in VRAM. It looks like a mess, but it allows the VDC chip to continuously read data of a single character. With that, we can use the hardware block copy feature very efficiently. Below that comes the rendering of the dungeon view. If you want to learn how generating a first-person view like this is done, please check out my video about the topic. Basically, drawing this dungeon view is related to how printing text is done. The tiles are arranged continuously in VRAM and block copy is used to put them into place. The difference to font rendering is that all the tiles have different dimensions, unlike monospace fonts. There is no transparency, by the way, so the dark background hides the fact that diagonal parts of the dungeon tiles just draw over it. To give an impression of movement, I changed the rendering order of the dungeon tiles. If we move sideways, the screen is either drawn left to right or right to left. When we move forward, the screen is drawn towards the player with the most remote tiles drawn first, and when moving backward, it is drawn with the closest tiles drawn first. Then we have the gems that need to be collected. The gems are drawn just as characters. Each gem consists of two of them, a left one and a right one. When we see gems around the corner, only one half is displayed. The code for that is messy as well, because my rendering code, again, was pretty much done from previous videos already, and when I worked on the gems, I recognized that it's a bit more work than I thought. Well, and in a game jam, you know, time is limited. And then we have the ghost. There's only one of them, and the algorithm follows what's documented about the original Pac-Man behavior of the red ghost. It always tries to catch you. I didn't find the time to implement the behavior of other ghosts. By the way, the game is not real-time, it's turn-based, so the ghost only moves when you move. And you will also see that there is no transparency here. So if the ghost appears in front of a colored background, you will see the black parts. Similar to tiles, I only wanted to display part of the ghost if he is just around the corner. I did that by using the same block copy command, but by changing the start address or the width of data to be copied. A very interesting question to answer was which side of the ghost to draw. Depending on which direction you're looking at it, you should see the correct perspective. There might be a smarter way of doing this. I just created a lookup table that contains the direction the player is facing and the direction the ghost is facing. Now, as a player, you can also attack or be attacked. When you attack, I just print an exclamation mark on top of the ghost. When the ghost attacks, the border is flashing red. And the VDC chip's scrolling register is used to briefly push the screen to one side. So much for the dungeon view. Below that is the high-res text display. The special effect here is that the text scrolls up. and that is also done by using block copy. The VDC just copies full scan lines to the previous lines and repeats this several times. The new line appears in full at the bottom. Speaking of copying line by line, when you start a new game from the main menu, the screen slides up just like a curtain, and behind it the game scene appears. This is done in the way that the full dungeon view is already rendered, but the VDC's screen pointer doesn't show it. And now, the main menu is copied up one scan line, and one line of the dungeon view is copied to the visible part of the screen. The VMC command is used for that again. Instead of reading and writing byte by byte for this copy operation, which requires 3 or 4 assembly instructions per byte, we just set up the copy source, copy destination, and number of bytes to copy. One line consists of 80 bytes, so we would have a couple hundred instructions for the CPU to execute. For block copy, we have, 20 instructions per scan line for the setup I just mentioned, so that's just a fraction. Compared to the C64, we not only can take advantage of 2 MHz, but also of a graphics chip that takes away quite some work from the CPU. And there are some more things to talk about when playing the game. When you hit the arrow left key, an overlay menu pops up. The black background is just a block fill operation over 63 bytes and repeated for 50 times. Drawing filled rectangles like that is really fast. The text is rendered as explained earlier. The animated cursor is also easy to do. Instead of only reacting when a key is pressed, we have a loop running now. Each iteration checks for a key press, and if none happened, it checks a timer. 3 times per second or so, it updates the character that's used for the cursor. And we also have an auto map, or a map actually. It's always fully uncovered, and it shows the player's location but not the ghosts. Displaying that map is also something worth mentioning. It is constructed at initialization time of the game, then it is stored into invisible VRAM. When the map is to be shown, it is just copied over into the visible part. You see, VRAM is used quite a lot in this game, and that's exactly the key to efficiently using the VDC chip. A block copy operation inside VRAM is much faster than copying the same data from main RAM to VRAM, or even from main RAM to main RAM. That brings me back to the main menu, and that's also an interesting part to talk about, especially because of the logo on top. That's not really special, I know, but this is the only asset in the game that's not permanently stored in VRAM. Whenever you leave the dungeon view and come back to the main menu, it is copied to VRAM on demand. And here it is first copied to an invisible part and then via VMC to the visible part. And this takes 10 jiffys maximum. Maybe this could be more efficient, but even in this way it's still fast enough to be not recognized by any player as a delay. The other entries of the main menu are pretty much text only, again with the animated cursor. There is instructions, also there is high scores, of course, and we can also redefine our keys, and there is some pages of acknowledgement. By doing it this way, I really wanted to mimic how DOS games have been done. I don't know, would you agree that C64 games usually just don't look like this? I'm open for discussing this. Let me know, you know where. Unfortunately, I wasn't able to finish Crawl 128 in time for the jam. And while I still kept working on it a bit, I had to stop myself all of a sudden because you could go on forever with little projects like these. But I decided to consider this done and start over with a fresh project to build more improvements. So I had one thing implemented, but that did not make it into Crawl 128 anymore: transparency. This is how it looks, and it is fairly fast if you ask me. I won't cover these details here, this deserves a dedicated video, Oh, and speaking of sprites, I know that some don't like the term to be used for sprites that are not done by hardware, as the VIC-2 does, but today the term has moved on from just describing a specific hardware feature, and it became a widely used term to describe movable graphics objects. And in my opinion, also the term soft sprite is valid, as it makes it clear whether the hard pixel heavy lifting on these old computers is done by the CPU or by the graphics chip. So yeah, maybe Crawl 128 is not a gem of game design in general, but it uses the VDC chip for some things that I have not yet seen in any C128 game. And considering that a lot of this has been built in BASIC, the C128 definitely has some benefits over the C64. I will continue building all kinds of software for the C128, fully leveraging on the VDC chip, so if you're interested in that, please make sure to subscribe. You will find links to everything in the description, including a download link for the game and the source code. Thanks for watching, see you next time here at the 8-Bit Theory.